I have only 20 minutes before this recording comes off. So the first thing is, we can reduce the space. Because notice that once I've computed this row, I'm never going to look at the rows above it before. So I just want to know the number here. Then I can throw the stuff away above this row once I've computed this row. So in fact, I'm only keeping one row. So I'm only using linear space. That gets me the number down here. Now, if I want the, if I actually want to find the sequence of edits, it's a little bit trickier, but we did that, we saw that a little bit in the last class when, yeah, we were keeping some list, I forget. But basically, you can keep, for these cells, you can sort of keep an idea of the edits, the best paths that get you there. And if you're sneaky about it, you can still sort of use it a bit. So the simple thing is you can compute the edit distance using quadratic time and linear space. And if you're sneaky about it, you don't actually need. But it's harder to use linear time if you're actually trying to get the strategy. You can do it. So, but we actually do align big things, and we don't do it in quadratic time because it would be insanely slow. So, I'm going to tell you about a trick. I have to start this again, except I'm going to run out of time anyway, so I won't start it. I'm going to tell you about a trick that you should know just for when it comes up, because it can make your program significantly faster. It's called banded dynamic programming. So usually when we're computing the edit distance between two strings, we're computing the edit distance between two strings which are similar. Because if they're really different, then we don't usually care how different they are. I mean, we don't compare random strings usually. Usually we're comparing like a genome of two humans, or a human and another mammal, or something like that. You're usually not comparing two completely different strings. So the thing is, if I asked you about the cost down here, okay? So I'm far off the diagonal. So here I'm asking about changing a string of length 5 into a string of length 1. Well, let's say, to make it interesting, into a string of length 2. Well, that's going to be at least, to change a string of length 5 into a string of length 2, you at least have to get rid of 3 characters. So the edit distance has to be sort of at least the distance from the diagonal, right? Because you at least need enough edits to make the lengths the same. So it means that everything that's far off the diagonal has high cost, right? The edit distance, all of these entries that are way off the diagonal have to be big. They have to be at least the distance from the diagonal. So if I tell you that the edit distance between Canada and banana is small, is say 3 or less, it's actually 2. But I say I'm not interested in what the edit distance is if it's more than 3. Then you don't have to fill in the parts of the matrix which are further than 3 from the diagonal. And so that actually, if I tell you 3, if you're sneaky, you can rewrite your program so that it only fills in this band along the diagonal. That's why it's called banded dynamic programming. And then if I give you the edit distance is k, you can actually do it in k times n time. I don't know if that will ever be useful to any of you, unless I put it on an exam or something. But sometimes, like, banded dynamic programming can really make your programs a lot more efficient in real life. And if you're doing things like computational genomics, which is important and like saves lives, it's important to know this kind of stuff. Okay, now I have like 15 minutes to teach you optimal binary search trees, which is a bit crazy. Oh, I have 22 minutes. Excellent. Except the camera is going to die because it's very hard to get SD cards, so I'm limited to 8 gigabytes. So it only records so many minutes. But we'll have the Collaborate Ultra. So, everyone knows what a binary search tree is, right? Good. If I were sneaky, I would get ready and ask a question just before taking a drink of tea. So, we saw in the lecture about Huffman's algorithm that you were trying to build an optimal prefix-free code, so you're trying to build a tree where you had weights of the leaves and the expected depth should be small. Well, suppose that somebody gives us a set of keys, but in a set of keys, and asks us to build a binary search tree. And we know the frequency for which they search for those keys. Well, we could just build a binary search tree, like any binary search tree, like you learned how to do in 2110. You could make it balanced, you could make it logarithmic type. Okay, so what is the worst case search time? It's like logarithmic. Okay, but that would be that might be suboptimal, because it could be that one of the keys, they search for one of those keys a lot. So if we were completely free, we would put that at the root. In fact, if this didn't have to be a search tree, we just had to put them in a tree, in a binary tree in some order, obviously you should put the most popular thing at the root. And the second most popular thing is one of its children. And the third most popular thing is the other of its children. And so on. So you would just build a complete binary tree, and you just fill it in the order of popularity. But that's not generally going to give you a binary search tree, because it's a search tree, it has to be lexicographically ordered. So, now, I'm going to check because, yeah, okay, this is good. I can open this. Good. Okay, so suppose I'm reading. I guess I could share this screen with you, but this is just the notes. So I wrote this last year. Here, I'll share the screen. So I think not last year. Well, yes, last year in 2019 when I was teaching the fall course. Okay. So suppose you're trying to build a binary search tree for can people see this? Why is my screen flickering? Okay, so we Apple, hide this. Yes, okay, people are going to see this. Okay. So we want to build a binary search tree for Apple, banana, grape, kiwi, orange, pear. So I'm always, this is an accident that before I was talking about vegetables and now I'm talking about fruits and I'm eating my breakfast. I'm not that obsessed with food. Maybe I am. But okay, so if apple has probability 13 and banana is probability 12, grape 15, kiwi 5, orange 12, pear 10, raspberry 8, strawberry 9. Okay, then the expected depth, apple, I'm going to get to apple. To get to apple, I'm going to do I'm going to go down 2 levels. But then, orange is at the root. So it's, 13. What's 2 times 13 plus 1 times 12? Oh, okay, no, sorry, banana is 12, yes. So banana is depth 1. So apple is depth 2, banana is depth 1, kiwi is depth 3. Okay, so the expected depth is 1.93. Okay, so if somebody searches in this binary search tree, the expected depth is 1.93. Can you do better? Can you rearrange the keys to get a smaller expected depth? Because then your binary search tree, you're going to, in general, the searches will be faster. Okay? So the greedy algorithm doesn't work. We don't have time for me to show you why it doesn't work, but it doesn't. But dynamic programming does. Okay? And I'm just going to switch this back. So, we don't have I don't have enough time to teach this properly. But the idea is, you're still going to use this idea of, you can ask, you have this weak-willed professor who will tell you the answer to some problems, but will just not tell you the answer to the whole thing. Okay? So you have, can we build BST where the in-order traversal will priority increasing order? But that would be not, no, in general no. Because here, in order, it has to be a binary search tree. So the keys have to appear in lexicographic order. Like in that example, it was apple. Apple starts with an A, so it has to be leftmost. So it's A, B, K, G, O, apple, banana, kiwi, grape, orange, pear, raspberry, strawberry, tangerine, watermelon. They have to appear in that order, and I'm not allowed to change the probabilities. So no, in general no. I mean, if they happen to, if the probabilities happen to be very nice somehow, then the problem is easier. But how so there's an easy way to do this. An easier, slow way to do this, and then if we have time, I'm going to show you how to do this. It's easy to see how to do this in cubic time, and then I'll try to show you how to do it in quadratic time, if we get there, if people follow me. So the idea is, you want to know what is the best binary search tree for those keys and those probabilities. But you don't know how to do this. But you have this weak-willed professor. So what you can ask the professor, well, your binary search tree, it has to have a root, right? It's going to have some key is going to be at the top. Okay? And then it's going to have a left subtree and a right subtree. The left subtree could be empty, and this could be apple, and everything else is in the right subtree, or the left subtree could be everything except, like, what was it, strawberry. So this could be watermelon, and this could be apple to tangerine. But empty subtrees are still subtrees. So, I'm not going to prove it, but it's not hard to figure out. If this is the optimal tree, so let's say that, pick something, raspberry. Suppose the best, consider all the trees that are rooted at raspberry. Strawberry to watermelon. Then this is an optimal tree for the set of keys from strawberry to watermelon. The dot dot dots actually just represent tangerine. These notes are posted on Brightspace under lecture 10. Yeah, so they're up there. This is also going to be, this is going to be an optimal tree for apple to pear. So what I'm not proving is that the subtrees of an optimal tree are themselves optimal. Okay, it's not hard. It's like, okay, suppose that you had a tree, you had an optimal tree, and one of these subtrees was suboptimal. If you replace it with the optimal tree for the keys in that subtree, then the cost doesn't go down. So the cost doesn't go up. It goes down. So, if you decide, okay, I want to root my tree, is this still recording? Yes. Wow. If you decide you want to root your tree at raspberry, then your left subtree will be an optimal tree for apple to pear, and this will be an optimal tree for strawberry to watermelon. Okay? So, somebody, I'm switching back and looking at the Brightspace now. So, how do you use your weak-willed prof to find the optimal binary search tree? There's a for loop involved. How do you find the optimal binary tree that's rooted at raspberry? Remember, you have this prof who will answer your questions about trees, of sets of keys of size up to size n-1. So, your weak-willed professor, I'm losing people already. Well, maybe not. Okay. Your weak-willed professor will tell you this is of size less than n, because even if this were empty, this is a key, so this would be size n-1. It's actually, this is not empty, this is size 3. You have a fourth key up here, so this is n-4. So you can ask your weak-willed professor, Prof, what's the cost of an optimal tree on apple to pear? And your prof says, oh, well, it's this. Right? And then you can say, oh, well, what's the cost of an optimal tree on strawberry to watermelon? And the prof says, oh, well, it's this. And so if you know that, say, this has probability 0.3, and this has probability, let's say this, ignore probability, this has weight 0.3, this has weight 0.1, this has weight 0.15, this has weight 0.15. Notice it's not like a Huffman tree in that you can just arbitrarily switch things because you have to maintain the order. Then you can say, well, if these are now a subtree, the cost of this whole tree is going to be the cost of the expected depth of this tree. It's going to be sort of this plus 1, because now you're taking this tree and moving it down. It's going to be plus this plus 1, and then this is at the root. Okay? So it's going to be the sum, it's going to be the cost of this tree plus the sum of the weights in this tree, because you're dropping it by one level, you're increasing all the depths by 1, plus the cost of this tree plus the sum of the weights, and then this doesn't contribute because it's multiplied by its depth, which is currently 0. Okay? So, if you've chosen, if you really want to have raspberry at the root, then you can ask your weak-willed professor